right, guys, so we're going to do notes 32A. We're going to have to do it in this weird cami way. I feel like it's going to be sloppy because I'm not used to doing it, but my board, my smart board, is not working right now. So this is going to have to do. So I want to just kind of quickly show you the kind of reactions we're talking about today. So today we are focusing on this kind of reaction. So thinking about it, we have a single on one side, we have a single on the other side. And that single is going to kick out what it's most like. So bromine, Br, is a non-metal. So it's going to kick out the non-metal that it's like, iodine. So bromine comes in, kicks out iodine, makes it single, and takes its place in the compound. So that's called a single replacement reaction. So I have a single on both sides, and the single replaces and kicks out the one it's most like. If it's a non-metal, it's going to kick out the non-metal, which is always written second. If it's a metal, it's going to kick out the metal. All right, so that's a single replacement reaction. We've been talking about that for 2.5 weeks, something like that now. Now we're at the end of our notes, 32A, and then we'll have 32B, and that's it. So single replacement reactions are literally all we're going to talk about today. That's it. We are focusing on these reactions. Okay, why I want to focus on them is because one element bumps another element out from a compound. Metals bump out metals, non-metals bump out non-metals. But how do they do this? Or when do they do this? Do they always do this? Does every single time I put a single element in a jar with a compound, they always have a chemical reaction? No, most things don't chemically react. So you have to know when a chemical reaction would actually take place. Why? What is happening that actually makes that reaction occur? So how we know is it says using the activity series and solubility chart. Tomorrow is a solubility chart. Today is activity series. So we are just using this activity series little diagram here, this arrow box, that's your activity series. And this says this is your activity series for non-metals. So just this little list. Okay, so you have this list for non-metals, you have this bigger list for metals, and that's your activity series we're going to use. Now, what it does, this series says in order to know whether an element has the strength to bump them out. Because again, I said, like, so if I put an element in a jar with a compound, do they react? Well, they're only going to react if the single element I put in has the strength to bump out the other element, meaning it has a stronger pull, like literally it's stronger, has a stronger magnetic pull where it's going to want to steal it away. So when I look at this example down here, I have potassium. Okay, so when I look at the periodic table, potassium is a metal. All right, so it's going to try to kick out copper. It wants to take its place so it can be in a stable compound. To know if potassium is strong enough to kick out copper, to take its place, we look at our activity series. We're going to see if potassium actually has a stronger pull than copper so that chlorine would want to ditch copper and go be with potassium. Okay, so let's see. All you do is you look at your list and you find the two elements in question, potassium and copper. So potassium is up at the top, strong element, looking good. Scroll down to find copper. Copper's way down here. Copper's pretty weak because this has a weaker pull. So this potassium definitely, being that it's up high, it says increasing activity, so it's getting a stronger pull as I go up the arrow. Potassium definitely has a stronger pull than copper does. So chlorine is going to be happier and more stable with potassium. It's going to feel that pull more, so we'll trade places. We'll have a reaction. So this potassium is going to go over and join with chlorine, or it's going to kick out copper. All right, so when I rewrite this, we're going to have copper by itself because it's been kicked out. See, I hate drawing. This is awful. I'm sorry. You have to listen to me as I'm saying what they are. Okay, so you're going to have copper, and it's going to be added to potassium is going to join with, okay, now how do I erase? Goodness. That didn't work. Why is it not erasing? Oh, there it goes. Okay, back to drawing. So potassium, like I said, is going to join up with chlorine. So we got potassium. It's going to join with chlorine. Now, the last part, you won't always have to do. Part of your worksheet is way simpler. So part of your worksheet today is just telling me which one is going to kick out. So if I gave you this reaction all the way done, you're going to tell me, is potassium strong enough to kick copper out? Would this reaction actually happen? And all you have to do is look at potassium, look at copper on the chart like we just did, and say, yeah, potassium's higher, it could happen. And that's it. You're going to circle which one's higher on the activity series. So that's easy. The second part is where you're trying to actually write out the equation. So like I just did, if it is higher, if potassium is stronger, then it's going to kick him out, make him single, and take his place. The last part, full credit, is to make sure that we have all the right subscripts. So to do that, remember when a single element is by itself, you ask yourself, is it part of the diatomics? So diatomics are way up here. No, it was here we go. So the diatomic elements were these 7. Is copper one of these 7? No. Okay, so then it doesn't need a little 2. We just leave copper by itself. That's all you have to do is when an element's by itself is you check your diatomic list. If it is in the list, then it needs a little 2. If it doesn't, then leave it alone. Now for a compound, you have to write their charges above them and balance them. So on the periodic table, potassium has a +1 and chlorine has a -1. Well, those balance. So I actually don't have to crisscross them. +1 -1 is 0. So that is the reaction. That's what would happen. And this reaction would occur because potassium is stronger. All right, let's do another one. So again, most of your paper is that simple. But then I did want to give you some harder examples. So because you do have a couple of those and you're going to get harder as we get into our lab later in this week. So now these are words. We're going to have to go from word to chemical formula to writing the rest of the reaction. So I'm going to go ahead, kind of just try to go a little faster. So we have aluminum, which is Al, nitrate, remember it ends in 8, not ide, so it's not normal. Nitrate is a polyatomic ion. Anytime it ends in 8 or ite, you got to go look it up. So what is nitrate? Nitrate is NO3. That's just what nitrate is NO3, like that. Now again, remember, when I have a compound, I have to write their charges to see if I need more subscript numbers. So aluminum on the periodic table is a +3. And nitrate, remember I had to look it up. It's polyatomic ion. So I look it up. What's nitrate? It's NO3 and it has a -1 charge. So those don't balance. So I do have to crisscross. So the 3 is going to come down to the nitrate like that. But I don't want it to be 33 oxygens. That looks weird. So I have to put this in parentheses. Okay, so we have that one wrote out. We're practicing our writing skeletal equations here. Add the plus sign. Join it with magnesium. Magnesium is an element by itself, so I just write its symbols. Magnesium symbol is Mg. There we go. But every time I write an element by itself, I ask myself, is it part of the diatomic? No. Magnesium is not part of the diatomic, so I leave it alone. And then I draw my arrow. Okay. Now, this is a single replacement reaction. Everything on today is. It has a single element. Magnesium is a metal, so it wants to kick out the metal, which is aluminum. So let's see if that can happen. Can magnesium kick out aluminum? Okay, here's magnesium. It's pretty high. It is higher than aluminum, just a little, but it's still higher, it's still stronger, so nitrate would prefer to be with it. So magnesium will take its place. So magnesium will get to kick out aluminum and take its place with nitrate. I'm going to run out of room, and this looks so awful. That's awful. It's MgNO3 is what that is supposed to say. There we go. Okay, and then we add it to what we just kicked out, which was aluminum. Now, same thing as I did before. If it's a single element by itself, is it diatomic? Does it need a little 2? Aluminum is not part of the 7, so I don't need a little 2. Leave it alone. For MgNO3, I got to write their charges and balance them. So magnesium on the periodic table is a +2. Nitrate is a -1. Okay, those don't balance, so the 1's going to come to magnesium. I don't have to write it. And the 2 is going to come down. And then again, we have that weird thing occur. I don't want 32 nitrates. I want 2 total nitrates. So I need a nitrate in parentheses. I know that looks awful, but it's Mg parentheses NO3 close parentheses 2. All right, and that's a reaction. That reaction occurs. All right, let's do another one. So barium fluoride. So we have barium, which is Ba. Fluoride is a regular. It's not fluoride or anything like that. So I just write its symbol, which is F. Remember that we have to write their charges and crisscross them if it's a compound. So barium has a +2 on the periodic table. Okay, I wrote that on top of it, but it's +2. Fluorine has a -1, so those don't balance. So the 1 has to come down, and the 2 has to come down. So the 2 is going to come to the fluorine, like so. I'm going to add that to my iodine. I'm writing an element by itself. Iodine's by itself. So anytime I write an element by itself, I have to ask myself, is it diatomic? Iodine is a diatomic. Okay, it's part of the 7, which means this iodine would never be without a partner of itself in real life. So iodine's only found as I2 in like nature, so it needs the 2. Then we're going to add it to, well, no, I lied. Goodness. Need to erase. Okay, and there we go, and we do our arrow now. Now, this is where we see if this reaction can actually occur. So I could actually ask you that question on a test. Probably will. Does this reaction happen? So again, you look at your single element. This is single replacement. Well, it's single. It wants to take its place, so it's going to kick out the thing it's like. Iodine is a non-metal, so it's going to kick out F, which is also a non-metal. It wants to take F's place. So let's go see if it can. Now, so far we've been looking at this list, but this is for metals. We're looking for non-metals. We're going to look at our non-metal list. Iodine is down here. It's actually the weakest of the ones we're going to look at. Fluorine's the highest. So when I'm asking myself this question, can iodine steal from fluorine? No, iodine isn't strong enough. So this reaction wouldn't occur. If I mix these two things together, they would not react because barium would prefer to be with fluorine. It's not strong enough. So you would say no reaction. I don't want to write out the word reaction with this weird draw tool. So I'm just going to put RX in for reaction. You can always shorten it like that. So that's no reaction. Okay, last question. Try to even complicate just a little bit more. Now you have a sentence instead of it telling you nicely this compound plus this single element arrow. So now you have to kind of read it with words. It says solid copper 1 iodide. Well, they're written together, so that is my compound, copper 1 iodide, and it says it reacts. Okay, so that's telling you the reacting is the plus. This is saying this reacts with this, so that's my plus sign, with chlorine gas. So that's chlorine by itself. Okay, so let's kind of write that down here. So we got copper, which is Cu. We have iodide, which is I. But it's a compound, so I got to do my charges with a crisscross. So this says it's a 1. That little Roman numeral tells me that this copper is copper 1, copper plus 1. Iodide, when I look up on the periodic table, is -1. So those actually balance 1 to 1. Plus 1 minus 1 is 0. So I leave those as is. Copper, or Cui. And then again, it reacts. So I put my plus sign with chlorine gas, which is just Cl. But remember, I'm writing an element by itself. This is my single replacement reaction. It's trying to kick them out. Anytime you write a single element, you have to ask yourself, is it diatomic? Chlorine is diatomic. It's on our 7. It's in our diatomic list of 7, so it needs a little 2. Okay, let me draw our arrow. And does this reaction occur? Okay, so chlorine is a non-metal, which means it wants to kick out iodine, the other non-metal. So let's go see if chlorine can. Okay, so chlorine's here. It's higher than iodine. So yes, chlorine is stronger than iodine. It can take its place. So chlorine is going to boot out iodine and make it by itself and take its place in the compound. So it'll be CuCl. Now, we still have to go back and make sure everything's correct. So I is by itself. Iodine is all alone, lonely little single element. If it's a single element, you have to know if it's a diatomic. So iodine is, we already knew that from the previous question up here, iodine is diatomic, so it does need a little 2. Now for copper chlorine, we know that copper is a +1 because it's still +1. It's still the exact same copper, same reaction. So it's still a +1. And on the periodic table, chlorine is a -1, which means they balance 1 to 1. So I actually don't need a crisscross. You don't need numbers down there. That's a reaction, and it would happen. Okay, so that's it. That's today. Okay, all right. So that's what we're doing today. And again, most of your questions are just like, can this beat out the other one? And you just look at your list and say, yes, it could, or no, it can't. And you circle which one is higher. There's only a couple of these down at the bottom. We actually have to write out all the steps. All right. You move me.